All right, I'm going to be a little bit rude in the sense that what I'm going to do is a continuing conversation with Pat that ended last June at the end of a dissertation defense with what I considered a question on the floor, and now I get to answer that question. But I'm going to spend the first few minutes trying to put the audience in a position where the question was asked and then give the answers. So the topic is indirect or derived measurement. That's measurements in which we assign values to one quantity. I'm only going to be concerned with physical quantity, by measuring something very different and using some kind of a theoretical principle or a theoretical assumption to infer the one from the other. So the examples, particularly the examples of primary concern to me as partly a historian of science, are things like using a mercury column to measure atmospheric pressure, using the length of a mercury column to measure temperature, using a particular spike on a particular kind of seismometer to measure the magnitude of earthquakes in the Richter scale. And the question that I've put a good deal of time into in the last few years is, under what circumstances do well-behaved results in the values for the inferred quantity give you evidence for the theoretical principle that's being presupposed in the inference? I'll wait just a minute. That this kind of evidence is important in 20th century microphysics is just so automatic that it scarcely needs to be stated. I've chosen one example from CODATA 2006. CODATA is the regularly published, I think it's about to be published again, it may be out, I don't know, committee on data that give the preferred values for the fundamental constants. In this particular case, what you're looking at in the graph is the inverse of the fine structure constant, starting with the 7th significant figure. So you're plotting different data and the uncertainty in those data from the 7th significant figure forward on a series of measurements. And the quote is the only place I'm going to quote. The good agreement of the highly accurate values of the fine structure constant inferred from the ratio of H over M for cesium and also for rubidium isotope, which are only weakly dependent on QED theory, with the values inferred from the electron anomaly, munonium transition frequencies, and the hydrogen and deuterium transition frequencies, provides support for the QED theory of the fine structure constant, as well as the bound state of munium, I'm sorry, I mispronounced that, and hydrogen and deuterium. In particular, the weighted mean, and now quoted, are two values, in one of them to 11 significant figures, the other to 12 significant figures, that are in remarkable agreement, in fact, in full agreement through the first 9 significant figures until you round the 10th from the 10th significant figure. And the remark made in the CODATA report is this is a truly impressive confirmation of QED theory. So I've been studying not just the CODATA use of converged measurements of fundamental constants, but the process that's gone on starting early in the 20th century with Perrin and has just been accumulating ever since. But my real interest in it and what got me going on it initially is not there, but in the very early stages of the history of physics, namely 17th century and Newton, which those who don't know me, that's my specialty, is Newton. You all know the first 2 laws of Newton, but I'm going to talk about them in a very different way. As they're used in the Principia, they serve almost purely a means to do indirect measurement. Indirect measurement of celestial forces to which we have no direct access, from changes in motion to which we do have direct access. So the first law of motion is best understood as it used in the Principia contraposed. What can you do with the first law of motion? You can infer the existence of a force. Then the second law of motion is used to quantify the magnitude of that force. The specific quantification that the second law uses, Newton explained in another place. I'm just going to state it briefly. I know those slides are hard to see. It's the mass times the limiting value of a certain distance divided by the square root of time as the time goes to 0. What's that distance? It's the distance between where the particle is, or the object is, and where it would have been had it continued in uniform motion in a straight line. And that limiting value, then the law asserts, is the magnitude of the force. And so you end up with a licensed inference from the limiting value of that quantity at any time to the magnitude and direction of the impressed motive force compelling the change of motion. And one of the real keys to the whole of the Principia, the revolutionary aspect of it in the history of science, is here put in italics, without any regard whatever for the mechanism producing that force. It's entirely a relation between two quantities, and laws are going to be formed in relations among the quantities. And I give you one quick example. Quite independent of the law of gravity, Newton's able to give the effect of the sun on the moon ratio to the effect of the earth on the moon to 5 significant figures purely from kinematic considerations. Now, there are philosophers, I don't think it's Pat, but there are philosophers, I should have gone back and looked at your axiomatization, so I apologize for not doing that. But there are philosophers who take the first 2 laws, actually the first 3 laws, as being implicit definitions of what the word force meant. And therefore, there is no issue of evidence about the laws of motion because they're defining what forces are. And if they're defining what forces are, there's not an issue. That's historically totally mistaken. Newton makes absolutely clear he's talking about everyday static forces. Forces that have been around from Archimedes forward. So there's a very strong empirical claim here, a claim relating certain changes of motion to the forces of statics and static equilibrium that have been around for generations. Looking now at the statics, the standard way, these by the way are 3 figures cleaned up from sketches of Christian Huygens, chosen intentionally for reasons you'll see in a moment. So the standard way of measuring one particular kind of static force, namely the tension in a string, is by the weight hanging on that string vertically, when vertical, or, as depending on the circumstances, that weight times the tendency to descend. And as the second figure shows you, if you put a weight on an inclined plane and balance it by a vertical weight on the other side, the vertical weight is significantly less, sine of the angle, times the weight of the one on the plane, because the tendency to descend on the plane is much less than vertically. So the whole idea that's all over the place, Mersenn's book on musical instruments does, of course, tension in musical strings. It's all done by weights. We still do it by weight very often, I think, when we do tuning. The interesting case, though, is the one at the bottom, which is a figure by Huygens in which he's doing 2 things. He's asking what the static situation is when you take something that's hanging vertically and lift it to an angle by pulling it sideways. And the question is, how much tension do you have to have in the string pulling it sideways for any given angle? Okay, he's also, in this you can see, those who can see it, the pulley at the top, he's also asking what's the tension, resulting tension in the string, showing that it is the familiar vector, what we would call the vector sum of the 2 tensions, but that's not the one I'm interested in. What I want to stress, and all of these results that Huygens has presented are totally standard. He knew of them from the work of Stevin, his countryman, who died before Huygens was born. They're called Stevin's triangle. These are just straightforward applications of Stevin's triangle. The actual result says the following: in order to get any in static equilibrium, any string to move vertically to any fixed angle, the tension has to be the vertical tension in the string times the tangent of that angle. And that's just a nice, well-established consequence of stemming. Okay, now there's a problem. Newton's talking about static forces and in motion. And the cases I just gave you of static equilibrium, there is no motion. So there's no relation between those as such and motion at all. And so the question of evidence can't be addressed unless there is indeed some case where static forces are in equilibrium, yet motion is involved. And that case was developed in 1659 by Christian Huygens when he developed what he called, he dubbed the word, his word, centrifugal force, by which he meant the centrifugal tension in a string required to keep an object in uniform circular motion. And you may not be able to see it, but his derivation is exactly using what subsequently became Newton's first two laws. That is, he's using the limit value of a displacement divided by time squared, taking that limit and discovering it comes out 4 pi squared times the radius of the string holding it divided by the period squared. So what he has done is not only to take a case of static equilibrium with a string, but he's taken that limiting value and turned it into something we can measure without having to worry about infinitesimals, namely the radius, the length of the string, and the period, both of which are comparatively easy to measure. So here was the vehicle that Newton knew totally well, the vehicle by which Newton could address the question, what's the evidence for his first two laws as assertions about relations between motion